Let's give some idea about the observational evidences for all these fluxes that we have been looking at. Typically, when these large field campaigns are organized, like Toga Core, in which Peter Webster was a lead scientist, or Jasmine, where he played a big role as well, and there are many other such campaigns in the ocean where aircraft fly, ships are around, moorings are put in, there are instrumentations done for a short time, for a long time, and so on. And the idea is always to learn processes focused on convection, air-sea interactions, Madden-Julian oscillation, and various other things. And often they are meant to come back and then improve the models somehow. There are lots of issues on how those things work. Nonetheless, if you just start with this Western Equatorial Ocean Circulation study that was part of the Toga Core from 1990, you can see that this is showing temperature and salinity, which is typically what we look for in the ocean. And you can see that they have identified these various axes along which data scatter. Oh, I hate this. And here is the diurnal heating, which obviously for a given salinity increases the surface temperature. Diurnal heating basically is sun comes up, ocean surface begins to heat, the water column gets nicely stratified, and ocean surface warms up. And then when sun sets, there is cooling, often strong enough to cause local increase in density and convection, or deepening of that turbulent surface mix layer that we talked about. And how deep it will get depends on how much energy there is to lift the cold water and mix it with the surface warmer waters that are typically gradient. There is a gradient between them. There is entrainment and evaporation. So I already mentioned the term entrainment, which means turbulent mix layer is going to entrain the heavier, colder water, which is going to cool the surface. And evaporation is going to have the effect of, as I said, leaving salt behind and causing convection and producing surface turbulent kinetic energy, which is what chews into the colder water below and causes the entrainment. And rain changes both the salinity, so decreases salinity, and typically decreases temperature. So this is kind of what is meant by the term SP, sensible heat of rain, that we talked about. Entrainment does also change salinity, but this, as we remember from before, depends on the barrier layer structure and so on. So typically in the West Pacific, where there is a lot of rain, there is a significant barrier layer, and in that case evaporation and entrainment depend on how strong the gradient is below the mix layer, and exactly how the mix layer itself is structured in terms of the isothermal depth and the isohaline depth, and where the entrainment happens. Because if the entrainment is happening from the barrier layer, the exact meaning of barrier layer is that it will create a barrier to cooling of the surface, so the entrainment may not cool the temperature too much. But you can see here there are directions where temperature cooling is order of a degree or more. Okay, this is how you would understand the processes. But these are very local, very synoptic scale observations. You can see that these are data collected on specific days in this period of 187 to 211, and you are putting them all together. To convert them into a global model, you have to understand if those typologies of processes are applicable elsewhere as well. For example, going from the warm waters in the West Pacific to the warm waters in the Bay of Bengal or the East Pacific, are they the same processes? Turns out not always necessarily the same. Just to touch on the attenuation of radiation in the upper ocean, the long wave radiation, you can see, is pretty much trapped to the top few centimeters, down to about 10 centimeters here. So longer wavelengths do not go too far into the ocean, and they can have a cooling or warming effect depending on whether it's a downwelling long wave from the clouds and the atmosphere to the surface, or upwelling or loss from the ocean surface. The incoming shortwave, on the other hand, has a broad spectrum in the visible, depending on the cloudiness, etc. And you can again see, depending on the wavelength, the longer infrared, near infrared wavelengths get attenuated very quickly, just as in this case. They are coming as a part of the shortwave band here, whereas this is part of the outgoing long wave band. But the blue and green can penetrate much further, and it really depends on how clear the water is. If for example, there is a strong upwelling, typically it brings nutrients, it creates photosynthesis and phytoplankton, and the phytoplankton tends to trap the radiation in a much shorter column of the water, and this can have an impact on the heat budget as well. So the penetrative radiation is a very important part of the heat budget and the buoyancy production in the ocean, which one has to keep in mind. This is from ship Ron H. Brown from the Bay of Bengal during the second phase of the Jasmine experiment, which is the joint air-sea monsoon interaction experiment. I think India and US were involved, maybe other countries, France maybe, I'm not completely sure. Oops, but you can see again we are looking at the data created by the ship crisscrossing this way. I suspect there was also a couple of Indian ships involved, and here is the Toga core array, which was done in the West Pacific much earlier than Jasmine. So this was completed by 1994, I think, whereas this one happened in 1999. This is just to figure out what are the differences between the warm water air-sea interactions and convection over here versus the warm waters and convection over here. Lots of interesting data was found. Typically they take the data and they put it on maps of data from other sources, like satellite, in this case going much larger latitude and longitude bands or days, and you are crisscrossing with the ship, and you can see the synoptic data being collected by the ship here, which is Lagrangian in the sense that ship is traveling and collecting data. So in this sense it is traveling as time is passing, whereas the satellite is doing it quite differently. So you want to merge as much data as possible to understand the processes, because just using ship data or mooring data, often you cannot complete the whole process understanding of entrainment, air-sea interactions, convection, and so on. So you can see here again data from I think reanalysis is being used in the background to look at winds and what else is shown, magnitude and direction of near surface winds during early May relative to the undisturbed weather prevailed during this. So this was basically done as a monsoon experiment, which means they have to be there during the pre-monsoon and the monsoon, so May into June and July. I'm not going to say much about this in the sense that you should be aware that such data are collected. They tend to be very local, very synoptic, and they provide incredible amount of insights, but the models which tend to have coarse grids and do not resolve these sorts of synoptic timescales and spatial scales have to be compared against data, and then some parameterizations are often derived for mixed layer entrainment processes, barrier layer structures, barrier layer processes, and then there is an attempt to improve models using these sorts of data. So you can see here surface heat fluxes during star 1. There is the diurnal cycle of the net solar that's clearly seen. Sensible is, as usual, very small, and you can see this is just a few days in both these cases. Okay, and there is the latent heat flux measured maybe by eddy covariance flux measurement from the ship and so on, and then net heat flux into the ocean in phase 2. You can see whether it's getting heated or losing heat. In this case, they reverse the sign in this book. So this is the gain of heat, and this is the loss of heat, and it depends on the systems moving in terms of cloudiness, rainfall, and so on. So the changes in net fluxes depends on whether there is a heat loss happening. So here, for example, there is a latent heat flux is going up and radiative heating is gone during the night time. So that's what determines at these kind of time scales what is determining the net heat flux. Salinity, temperature, etc. are measured into the ocean as well. So then comparison of the energy balance of the Western Equatorial Pacific Ocean and Northern Indian Ocean is done between two different periods. So this is November 92 to February 93, and this is April to September 99. Obviously there is a strong seasonality, especially in the monsoon region as well as in the Western Pacific. Nonetheless, some idea is derived from the various comparisons to see how the mixed layer heat budget and the process of SST control at these typical subseasonal to synoptic timescales or synoptic to subseasonal timescales may be happening. I will leave this here and come to mixed layer heat budget in the next podcast. So just remember that there are numerous attempts, not only by observations where ships have to go, aircrafts have to fly, but there are also now moorings in the ocean which permanently stay there. Some of them measure just temperature, some of them measure temperature and salinity, some of them measure temperature, salinity, and currents. Some of them also measure surface fluxes, winds, humidity, radiation, precipitation, and so on. So those are very useful, but tend to be very local and synoptic. I don't mean it in a bad way. I'm just saying, as a modeler, it's always a challenge to translate that information into model space and then validate the model, especially when we said fluxes have errors. When a model does C-surface temperature wrong, you have to be sure that that error can be attributed either to the surface flux that may have an error or the model process that may be not done properly in the model. So that kind of attributing error is not always easy.